Hey guys, this is Vic here, and today I'm going to talk to you about the shunt equation. So what is the shunt equation? It's an equation that attempts to define the extent that venous blood bypasses oxygenation in the capillaries of the lung, or effectively define the amount of blood that is shunted, and it can also be used to describe VQ mismatch. The technical equation itself relates the percentage of blood flow that is not exposed to inhaled gas compared to the total blood flow, or specifically the shunt fraction. So that's the cardiac output which is shunted compared to the cardiac output which enters the lung. Obviously this is difficult to purely measure cardiac output and blood flow, so the equation uses the surrogate of oxygenation to work backwards to figure out the shunt fraction, and the oxygen used is the venous, arterial and capillary oxygenation. So that's the shunt equation below. The easiest way to do this is to explain this is actually to show how the equation is derived. A normal shunt is around 4 to 10%, so any higher than this indicates that there is a VQ mismatch going on. And an important assumption is that the pulmonary capillary O2 is roughly the same as the alveolar O2 for purposes of calculation. Where does the equation come from? So we'll attempt to derive this. It is a bit mathy and technical, but the principles are reasonably important. So when blood enters the pulmonary system, it will have a net oxygen movement of the oxygen content of the venous blood entering multiplied by the cardiac output, or the total amount of blood entering. This is represented by QT times the concentration of venous O2, and conversely blood leaving the pulmonary system will have a net oxygen flux of the oxygen content of arterial blood multiplied by the cardiac output, or QT times the capillary, so the concentration of arterial O2. The total cardiac output through the lungs is equal to the amount of blood that goes through the pulmonary capillaries added to the amount of blood that goes through the shunted areas of the lung, and this is represented by the equation below. So QT total equals flow shunted plus flow through capillaries. If we rearrange the equation to make the capillary blood flow the subject of the equation, we get the following equation, and then if we combine this equation back into the oxygen content equation, we get the following equation. So the total blood flow times the arterial oxygenation is equal to the shunted blood flow times the venous oxygenation plus the difference between total and shunted blood flow times the capillary oxygenation. Then we do some fancy maths, multiply some brackets, get the terms on the same side, and then remove the blood flow, and we end up with the shunt equation. So the shunted fraction is equal to the difference between capillary and arterial oxygenation over the difference between capillary and venous oxygenation. Nice and easy, isn't it? So just in case everyone is as confused as I was when I first looked at this, I'll go through it one more time quickly with the aid of a picture. So this picture here represents the blood flow through the lung. The first bit is the blood flow that enters the lung and has the following oxygenation. Then you have the blood flow that goes through the lung, and that is represented by a fraction which is shunted, and an area that goes through the pulmonary capillaries. And then finally you have the blood flow that leaves the lung. We would like to figure out the fraction that is shunted, or the ratio between the shunted blood flow to the total blood flow. Unfortunately, we can't do this without invasive arterial monitoring, venous monitoring, and pulmonary capillary monitoring. So we use the surrogates of oxygenation. By doing some fancy math, we can figure out that the amount of oxygen which should be added to mixed venous blood is represented by the difference between the pulmonary capillary and the venous O2, and that the amount of oxygen which is actually added to the mixed blood is the difference between the capillary O2 and the arterial O2. If we take both these values and then substitute them into the equation, we can then figure it out what exactly the shunted fraction is.